Well, hello everybody, and welcome back to the Australian Corrosion Association's Corrosion and Prevention Conference online. For those of you that have just joined, my name's Justin Rigby. I'm chairing this session and introducing the speakers and helping you along during question time. So it's my pleasure to be here. Our next presenter is Dr. Eric Ferguson. Dr. Eric is a senior machine learning engineer at Abyss Solutions, and he was awarded his doctorate in engineering from the University of Sydney in 2019 for his research contributing to the fields of machine learning and signal processing. Today, he will be presenting a paper on automatic detection and classification of corrosion with convolutional neural networks. So I now welcome Dr. Eric Ferguson.
Thanks very much, Justin. Appreciate the introduction there. Well, thanks for everyone for joining us today. As the introduction says, I'm Dr. Eric Ferguson, and today I'll be presenting a paper on the automatic detection and classification of corrosion with convolutional neural networks. So my co-authors and my co-authors that you can see on the screen there, my co-authors and I, we're a series of robotics engineers, computer vision experts, machine learning engineers, and we're working out of Abyss Solutions, which is here in Sydney, Australia. So a lot of what I say today is going to be colored by my experiences in developing new technologies for the oil and gas industry, and particularly that's with the context of oil and gas offshore platforms. And so, in fact, the technology that I'll be demonstrating today is actually demonstrated on a large offshore platform. It's like 10 to 20,000 tons topside, which is in the Gulf of Mexico. And so I'll sort of be trying to provide some context for this technology and this research from that sort of angle. So there's this concept in managing of these offshore facilities called fabric maintenance. And fabric maintenance, one of the primary goals for it is managing and detecting the onset of corrosion across the platform surface. And so this continuous fabric maintenance, it's absolutely crucial for the uninterrupted operations of offshore oil and gas platforms. And so currently, how it sort of goes about is, physical field inspections with subject matter experts in corrosion, inspectors. They physically go out and do these corrosion detection campaigns, these corrosion classification campaigns, and sort of try and get an understanding of the corrosion across the facility, across the assets, across the equipment. So unfortunately, how it's currently done, some of these processes, they can be subjective between from one inspector to the next. For example, classifying how severe a particular instance of corrosion is, there can be a lot of differences in opinion there. It's also costly, time consuming, it's labor intensive. And as such, because of these factors, inspections tend to be sparse in nature. So what that means is that they provide incomplete asset coverage or provide an incomplete understanding of the facility that we're inspecting. So this has knock-on effects upstream, such as increased risk of unplanned platform shutdown, increased personal risk, increased environmental risk. Perhaps there's a high pressure oil pipeline. If we get corrosion on that and we fail to identify it, that could be subject to fail. And then, of course, the environmental catastrophe that comes along with that. So detecting corrosion, finding corrosion, associating corrosion with individual pieces of equipment on a facility, very, very important. So when we're doing an inspection, we're sort of acknowledging some of these weaknesses in the physical field inspection. And really what we want to be doing is proposing a new solution that's able to answer these important questions. So first of all, we want to know where the corrosion is. So we can see on the left here, we've got an inspection image. Where's the corrosion? Also, how bad is the corrosion? So this can be things like, is it just a light scale, or, some deep pitting, some deep penetration into some pressure equipment. So that's the severity. Also, how big is it? So that's the physical area. Maybe this is a meter squared, and that can help inform us some of the how much remediation we have to do. Another additional thing that we'd like to do is actually associate corrosion to the equipment that it is that it's on. So, you know, and that empowers us to be able to say, hey, you know, I really want to concentrate on bad corrosion on this particular pipeline because it's high risk. And then finally, we really want to be able to trusted technology solutions. So we want complete coverage. We don't want to miss anything on a facility. Also, we want accuracy. You know, we want to be able to quantify exactly how much we can trust algorithms like that. So ideally, what we want is this image that you can see sort of fading in on the left-hand side. This would be brilliant. You know, these sort of highlighted masks or polygons there, they're highlighting corrosion, instances of corrosion in this inspection image. So we've got blue here, which is might be some light scaling, medium, which is medium severity, yellow, which is medium severity, and red, which is, you know, the really bad stuff, heavy corrosion. So if we could get this, then this would be absolutely brilliant. So that's a bit of context. I'm going to switch gears a little bit for a moment. And a current technology, you know, a semantic image segmentation via convolutional neural networks. Now, this has been an absolute, this has been a focus point of scientific research in image processing and scene understanding at the moment, and also in recent years. So this is used in things like self-driving cars. So you can see in the lower right there, you know, we're highlighting where the people and the cars are. It's used in the medicine fields, you know, detecting cancer, things like this. And it's basically, instead of holistically classifying images, so saying this image contains a dog or this image contains rust, we're actually dividing the image up pixel by pixel into its important parts. So what that basically means is, if we were to do that to the inspection data, for example, this would give us a very, very detailed understanding of the scene, very detailed understanding of the inspection data. So you may have heard that machine learning, it's a very, very data hungry business, and it requires a lot of very, very high quality data also. So there's been a drive, particularly in oil and gas, but also in other sectors, to move from the analog or manual management of facilities or systems into digital management. So this is the concept of, you know, a digital twin of your facility, which can help help manage it, And so it's increasingly common to go out and collect this inspection data, this spherical imagery that you see on the left here. And so this is a 360-degree panoramic, you know, you can see all around you. And then also go out and collect laser scans. And so what laser scans, when they're accompanying this data, it also now enables us to make physical measurements of things. So that's saying, I don't know, this pipe is 0.5 meter in size, or this corrosion instance is, you know, 1 meter squared in area. So laser scans are also very important. And so what we can do, it's not just one scan, but we can go out and collect hundreds across a platform or a facility, and use that to get sort of a comprehensive coverage, comprehensive understanding of this facility that we're trying to analyze. So another important thing about machine learning with our convolutional neural networks that we're using to try and develop a solution, it requires a training data set to learn from. And so in this data set, we have examples that we use to teach a convolutional neural network, a CNN. We have examples to teach this CNN some understanding of what corrosion is, what it looks like, and also how to detect and how to classify that corrosion. So with the use of inspection and corrosion subject matter experts, they can actually help us create a training data set which can depict corrosion in its various states, and try and capture that expert knowledge that these experts in the industry have, and teach that to our neural networks. So you can see here, for instance, on the left, this is an example of a training image where we've highlighted regions of the image where there is corrosion. So the blue there, we've classified the categorization as less than 2 millimeters thick of scale. The yellow, which is medium severity corrosion, and then we've also got the high, the red, which is like severe corrosion, which is, where things really start flaking, degrading, more than 5 mil thick. So this is just an example of how we can sort of bin or discretely categorize up the corrosion into different severities. So we get a whole bunch of images like this. We train a convolutional neural network to detect and classify corrosion in each pixel of this inspection imagery. And so how do we go? So we've trained a network, and now we're applying it directly to the inspection data that we've captured. So we're using the semantic image segmentation via convolutional neural networks. So on the image here on the left, we can see that there's been 3 severities of corrosion detected. And so each pixel in the inspection imagery, it's classified into this light, medium, and heavy. And this happens across every pixel of the inspection data. So it's an enormous data problem. So in the blue, we've got the light severity. In the yellow, we've got medium. And in the red, we've got severe. And then now you remember, coupled with that laser scan data that we also capture at the same time, we're able to do the physical measurements. So we can see this particular instance of light corrosion in the on the railing there has an area of 0.1 meters squared. So we end up having a comprehensive solution because we've got lots of different lots of data points to search through, a comprehensive solution. But another great thing about machine learning and moving things from, I guess, the physical space into software is we can make things fast and scalable, which is very, very good. So this is a massive data problem, but we can pump all the inspection imagery through the machine learning networks and basically discover a lot of insight very, very quickly as to the health of our facility or the health of our equipment. Another good thing about machine learning is the more you deploy it, or the more that its training data set expands over time. Maybe instead of Gulf of Mexico, we start deploying in the North Sea or something like that. It gets exposed to more and more examples and different modes of corrosion, I guess, and so the models improve over time with each subsequent deployment or continued use of the models, which is another accurate thing. So in this particular instance, how well did we actually go? So this matrix, I guess, may be a little bit hard to look at, but the key numbers are, in terms of detecting corrosion, we were able to detect, in this particular instance, greater than 90% of the corrosion present for all the corrosion on this facility, on this large facility that we're demonstrating on. So that's 90% of the corrosion. You can see also that we may not have been able to classify it correctly all the time, but we've only missed one instance of severe corrosion, which is incredibly important. We don't want to miss any severe corrosion because that can pose a very, very high risk to the asset owners when they're going out and actually trying to fix this corrosion once it's detected. So I mentioned before also that we've got these hundreds of capture locations across a platform or deck. Because we know the location of each of these capture locations, we can actually start looking at individual pieces of equipment from multiple different angles, and this is incredibly powerful. So you can see here this in this central image, this sort of lower left-hand side, the convolutional neural network has detected some red corrosion on this flange pipe combo here. In the other instances, from other different angles, it's detected some medium and light corrosion. And so what you end up getting is, sort of a 360-degree view, lots of different angles, lots of different ranges, so you can build up a comprehensive understanding of individual assets, individual pieces of equipment across the entire facility. So combining things spatially, not just looking from one view. You can't see the backside of a flange, for instance, in an image. Combining these all spatially gives us a comprehensive understanding of the equipment. So let's put all this together. So we've been able to detect the corrosion, we've been able to classify it, we've been able to do a decent job at doing both of those things. It'd be great if we were able to actually associate that corrosion with individual pieces of equipment. So often a lot of these facilities, particularly new facilities that come in, they have digital twins. And so a digital twin is basically a digital representation of the facility at hand. So we can overlay any inspection data that we have, overlay that with this digital twin, and start actually associating detected corrosion, the onset and the severity of corrosion, to individual pieces of equipment, which is incredibly powerful. So you can see here in the lower right-hand side, another example of a flange here. This is sort of shown from 3 different angles. We can see that this is equipment tag, 401033. We can see that we've detected 5 centimeters squared of light corrosion here, and 50 centimeters squared odd of medium corrosion. And so that's from looking at all angles, understanding it holistically, the state of this flange. Indeed, you can also see that there's 38 different angles and ranges that this flange has been inspected from. So that's a really great benefit of getting comprehensively collecting data to give us a comprehensive understanding of of what we're looking at. So now we're able to actually associate the corrosion with with individual pieces of equipment. What that can also lead to is we can actually have a database to start managing all the anomalies or all the corrosion in this instance across assets. So you can see here on the lower right-hand side, because we have all the equipment tags, we can start having this sort of searchable database and looking fine-grained at individual pieces of equipment. Perhaps we want to sort and say, oh, there's a high-pressure gas line. It's got show me all the stuff with severe corrosion, so I can remediate that and go fix that first. That's we're able to target that by putting everything in a database and then searching it. It's incredibly powerful if you're able to search through your data and your analytics. So that's the fine-grained approach. Also, you can collate all this data into a more holistic understanding of the facility. So you can see here on the right-hand side, there's 1,400 odd lines here. 2/3 of those have some form of corrosion. A third of those have heavy corrosion on them. So this could be an example of regions that we want to remediate first, or particular attention needs to be addressed. So being able to not only detect things accurately, but then also associate that physically to help management is an incredibly powerful thing to be able to do. So thanks very much. I'd like to open up to questions now. And of course, if we don't manage to cover them all, please feel free to reach out, and my email's on the screen. Thank you.
Excellent. Well, Eric, very good presentation. There's a lot of information there to understand. So we do have one question here. How was the severity of corrosion determined prior to training the model? Yeah,
so that's excellent. So I'll go over to this categorization thing here. So how we're determining the severity is very similar to doing a general visual inspection of the area. So that's looking at the visual appearance of the corrosion and then sort of categorizing that. And you're right, it's a very, very difficult problem also to do, to actually categorize these things. So one of our, when we first started looking at this sort of technology, an issue that we came across was we were talking to corrosion experts, subject matter experts, and no one agreed on what was medium, what was high. It's just looking visually at the corrosion. It's a very difficult problem to do. So one of the benefits actually of this system is it alleviates this subjectivity as well when you're looking and identifying corrosion, and makes it more objective. So it's almost like you've got one inspector categorizing things rather than multiple inspectors giving different answers for the same instance of corrosion. Hope that answers your question.
Yeah. Okay. So essentially, you're using spatial technology to take a whole heap of imagery. You're telling the machine what you determine as being heavy or light rust, and then you need to make an assumption as to what how deep heavy rust is and how deep light rust is.
Yeah.
And that leads me into another question from Brian Kinsella. How was the metal loss quantified, or is it based only on appearance?
Yeah, another great question. So in this particular paper that I'm presenting here, it's based purely on visual appearance. Except, maybe I'll be presenting a new bit of research next year to you all, where we can actually use that laser data to physically measure this metal loss, and also indeed physically measure the amount of scale as well. So this visual appearance, it's a very qualitative approach. When you start incorporating the laser in there to physically measure the amount of metal loss or physically measure the thickness of the rust, that's a quantitative approach, I guess. And that would be an extension, which I'm sure I'll be presenting to you next year.
Yeah, sure. Another question, how many images did you use to train the model?
Yeah, it's a great question. So there was a previous research paper made, would have been 2 years ago. Pardon, I can't remember the authors, but they estimated that you'd need tens of thousands of images to train a good network, and obviously it's very labor intensive to actually make these training data sets. You got to make these masks for each individual pixel for your training data set. You can actually use other techniques in machine learning called things like active learning, where you try and find hard examples which are more informative, I guess, to your network. So if you train a network on the harder examples rather than the easy examples, you need less images at the end. In terms of how many images there are, it changes every day as this sort of technology gets deployed on more and more facilities across the world.
Sure. Another question, can it be used to detect corrosion on moving equipment such as trains and vehicles?
Yeah, another great question. And it's difficult to answer. So, I mean, for all intents and purposes, hold on, I'll try and show, where's an image? When you go out and capture this, I mean, it captures a single point in time. So, since you're detecting corrosion at that single point in time, so as long as your imagery isn't blurry and you can actually see the rust in the images, then there's no reason why you can't do it on moving equipment. Indeed, another extension, which is not present in this paper, we've actually used drones to go out and try and detect corrosion. And so you're doing it on the video there, and we've been successful in detecting the corrosion in this video, for example, of moving parts.
Fantastic. Another question, how do you differentiate deposits from corrosion scaling?
Yes, great. Another great question. And I'm not too sure at the moment. I'm not afraid to say it. I mean, this sort of machine learning. Hold on, let me pull up an image. These sort of machine learning technologies, they're very, very good at what you give them in their training data sets. If you start giving them examples that are outside their training data set, then they'll perform poorly. So basically, you want your training conditions to match your deployment or operational conditions. And so what I would say in terms of that is you'd want the network to behave in a particular way. So then you'd give it examples of that particular problem. Say, for example, distinguishing deposits. Yeah, a great question.
Yeah, I think it seems that this is an exciting technology, and we are moving towards digitalizing our assets, aren't we? So this is exciting technology whereby you're able to, like you said, objectively categorize different regions of corrosion, but we're still categorizing them to a visual standard before they need further investigation to determine pit depth and things like that.
Yeah, that's right. So thinking of this particular instance as I guess a rapid general visual inspection is a really, really good way. So, a really good way of thinking of it, in that perhaps it says, look, this pipeline, it's in a horrible state. we need an inspection team to go out and really quantify exactly where and how this pipe can fail. So it's a great technology for pointing out, where we should be focusing our remediation and inspection efforts further.
Yeah, just looking at the huge amount of data that you had there, 1,400 entries and thousands of images, and being able to put it into a format that you can read.
Yeah, that's it.
Couple of questions. Have you thought about, like you've done one inspection now in a year or 3 years or 5 years, when you do another inspection, how you can overlay the data and see how an asset is getting better or worse?
Yeah, looking at say trend analysis, or another powerful thing that would actually open up is detecting the onset of corrosion before it's almost actually it's predicting it, basically. So predicting where your problems are going to be next year. I tell you what, that's something that we'd love to be looking at. As such, we actually haven't had 2 subsequent inspections to actually start developing this technology. But I mean, very soon at Abyss, we're actually going to be doing a second inspection on one of our platforms, and we'll begin developing exactly that. And I think that that's going to be a really exciting new bit of technology and research that's going to come in the future. Sure.
One point here is, it keeps moving around on me, is that how do you find detecting corrosion on stainless steel as opposed to mild steel?
Yeah, another good question. So again, it sort of goes back to the to what you're putting in your training data set. So if you're classifying, say it's on stainless, if you're saying that is light, and it has a slightly different visual appearance to, say, when you're putting it on mild, then you will be able to categorize that as in a separate thing. So how you sort of discretize up your, so let me pull up this table here. How you sort of discretize and break up your problem into separate bins, I guess. It's really, I mean, so I come from industry, and so how we do it is heavily driven by how the client wants us to do it, how it's how they have their existing inspection processes. So if you needed to say, oh, this corrosion is on stainless, then perhaps you could have a fourth category rather, saying, hey, detect the stuff on stainless based on visual appearance. But a good question.
Yeah. And Dr. Anthea Airy, pitting corrosion, is this being related to external visually detectable scale?
Yes, it is. That's exactly right. So at the moment, these, I'll actually highlight this, where is it? So you can see here, for example, on high, which is the lower part of that table there, you can see scale greater than 5 mil thick, but it's also estimated metal loss less than 5 mil thick. So at the moment, we're categorizing them together. It's a great point that you bring up, and one that is eventually addressed, not in this paper, but eventually addressed by looking at the laser scan data and actually saying, is this a blister swelling up, or is this metal loss? So you can actually categorize further if you wanted to, and something that I'm sure I'll be presenting next year to all of you.
And when you're doing that, are you, so you identify the areas with 5 millimeters of scale,
Mm-hmm.
then do you go around and chip some of that away and measure pit depth?
No, not at the moment. So at the moment, it's based purely on visual, the visual appearance of it. That would be an excellent thing to do.
Yeah, sure.
Yeah.
Not everybody lets you do that.
No, that's exactly right. I mean, it's another, like, physically, I guess, validating these things, and and one method being exactly as you said, Justin. Great way to do it, but they've got to let you do it. That's the problem.
Probably a final question here. How often do you activate the lasers? Are they fixed in place between scans?
Yeah, so what I'd recommend looking up if you are interested in the actual data capture technology, a lot of this stuff's off the shelf. So there's companies like Leica, Z&F, they make these 3D terrestrial scanners. And what they actually do is they capture the visual imagery at the exact same time as they captured the laser. So, maybe you put this thing on a tripod or on a robot, whatever you're doing. It'll sit there, do a scan, 5 minutes, 10 minutes, depending on the quality, and then you'll get the laser and the visual image from that during that capture, I guess.
Cool, excellent. Well, it sounds like we're all ready for this technology. We just need you to catch up.
That's it.
Yeah, it's all new technologies are like that, right? You've got to start somewhere and learn as you move forward.
That's exactly it. It's really exciting. Slowly looking at this, being adopted by the industry. So it's definitely an exciting pathway, research pathway to be undertaking at the moment.
Looks like it will be a great success. So, Dr. Eric, I'd like to thank you for your presentation. Do you have any closing comments?
No, actually, but feel free to reach out if you do. If anyone has any additional questions, my email is there on the screen. Happy to always talk technology. So thanks very much for your time. Thanks, Justin.
No worries. All right, everybody. Well, thank you for being online. We're going to take our next break and we'll have you back in 15 minutes for the next presentation. Thank you.
Thank you.